So Faraday's law applies to any situation with a changing B field. So let's just draw a bunch of cases. It'll be good practice to kind of give us a feel for Faraday's law. So first I'll just draw a current loop here, or a loop of wire, and we'll say, okay, it has to have an area vector. We have to decide which way is positive, basically. And then behind it, I'll draw a bar magnet like this, like that, where this is the North Pole and this is the South Pole. And this is similar to the demo we did. We were pushing a magnet through a bunch of coils. Let's see. So we know that the magnetic field comes out like that, and like that, and like that. So it wants to go from north to south. So in this case, the magnetic field is coming out of the loop in the same direction as the area. And let's imagine that the magnet is moving that way. So we have the North Pole moving towards a loop. Let's think about what Faraday's law tells us will happen. Well, we have a case where the flux is changing because the strength of the magnetic field is large right near the pole and it gets weaker as you go away. So if you move a bar magnet like this near a coil or near a loop, it will change. So let's look then and think about it. d phi b dt is what here? Here it's positive. So you got to think about the rate of change of the flux. So if we have this loop getting closer to the magnetic field intensity is bigger here than it is here. So if we move towards the bigger part, then the b dot dA here is weak, and as this gets closer, it'll get bigger. So d phi b dt is positive. So according to Faraday's law, the EMF is negative. Well, what does that tell us about the direction of the current? Well, we have to decide what is the direction of positive current. We decided that when we chose the area vector. Okay? We made the area of the loop positive this way. So if you apply the right-hand rule, you say, okay, positive current is this way, from the front of the loop going towards the back of the loop. But the EMF says it goes the other way. So the current in that case would go from the back to the front. So that's pretty much what would happen. But now we can compare different kinds of cases. What if we had the same thing, loop, area vector, magnet, like that, but now we have the South Pole here and the North Pole here, but we still haven't moved towards the loop? Well, now the field lines will look kind of the same, kind of like that, and kind of like that, except now they're pointing in, right? The field goes from south to north. But we have the area vector going the same way. So now the flux is negative. Okay, so d phi, the flux itself, the value of the flux is negative. But as we move this closer, you get a more and more negative value. Right? The flux is going down. So the rate of change of the flux is negative. Not only is the value of the flux negative, but it's getting larger and larger negative magnitude. That means its rate is also going negative. So when you just do these problems thinking about them, you have to keep up with what is the magnitude of the flux and what is the rate of change of that magnitude of the flux. It's tricky. So anyway, if that's negative, then according to Faraday's law, there's a negative sign, so the EMF is positive. If the EMF is positive, then the current will go in the positive direction, defined by the area as that way, from front to back, like that. We'll go around. Okay. Let's do one more, just to seal it here. Let's see. There's a loop. Again, we're putting the area this way. This is the front. That's the back. And we have bar magnet north-south. We'll go back to our original bar magnet, but we'll make it go that way. Now let's pull the magnet out. All right, so the field lines go like that, and this field line goes like that. Okay, they go out because we're at the North Pole. So now we're pulling it away. It's going from some high flux, a lot of field lines going through, and when you pull away, less field lines will go through. On all these, the way I'm drawing it, it looks like you're going to retain 4 field lines. Keep in mind, these are not technically perfect field drawings. So understand that here the field intensity is high, here it's lower. So we're pulling away. So when we pull away, we have, let's see, here we have a positive flux, but it's going from high to low as you go down. So d phi b dt is negative. The flux is decreasing when you pull that thing out. If d phi b dt is negative, then the EMF that's induced is positive. Area is that way, it's this way. Same as this condition. So you can see the EMF you get, it depends on many things. It depends on which way the B field is, whether the B field is going up or down, north, south, south, north. All these things can flip it back and forth. This is not the only way to induce an EMF. We can draw many other interesting situations. We could have a current loop here. So let's put this thing, send some current into here and out here. And let's make that current vary in time, some time varying current. And then we could put our loop, our other loop, nearby. Okay? So we know what this thing's going to do. This loop is going to make a B field. Let's see if the current goes around like this, then it's going to have a B field pointing out like that, like that, and it's going to go like that. So this current loop that's having current driven in it at some time varying rate will generate a B field inside of this loop. And let's see, the way I've drawn it, let's say that di dt is positive. So let's say the current is increasing at some moment in time. Then this B field is positive. B field is increasing. Let's define this area as out. Let's say the area goes that way. So you can't see it coming to that surface right there. And these are all B lines out here. If that's the case, then if b dt is positive and it's the same direction as the area, then d phi b dt is positive, so the EMF is negative. Let's see, so if the EMF is negative, then this is the way around that gives you the positive A, so the current will go that way. So the current induced is the opposite direction as the current that did the inducing. So we'll see more things like that later. There's lots of ways to do this. Let's have a current going along a wire. Let's see, right-hand rule, current's that way. It's coming out of the board here, big field here, and then it gets weaker as it goes away. So remember, it circles around. And it gets weaker. There we go. What if we just have a current, a wire loop and just let it fall due to gravity? Or just say let it move down. Well, it's got a changing magnetic flux through the loop. It's going to experience an EMF. It's going to have an EMF induced in it. We can think about, without writing it out, the direction. Let's see. If we define the area vector out this way, so that way is positive, the B field is going in against the area vector, so the flux is negative, but it's getting smaller. It's negative and getting smaller, so d phi b dt is increasing. It can be negative, but increase. Positive EMF, therefore, is negative, and if the EMF is negative, then that's the positive direction the current goes that way. Okay. You can always get there. I know you want to see one more, because I got to fill the board. Here is a piece of iron that, as we talked about, is a ferromagnet. So if we take a coil and wrap it around this iron and send a current as a function of time through that coil, it will align the magnetic domains in the iron. It actually will do it all along the iron. So often ferromagnets are used to sort of control a magnetic field in space. If we put another coil, it looks just the same here. We could ask ourselves, what kind of a current is induced? Well, let's see. So here, this current is going around the back, and in the front, it's actually making a field this way if the current is positive. So let's see if di dt is positive. If it's increasing, then that means the magnetic field dB dt is increasing, is positive if it's going that way. And let's see if we assign A positive this way for each one of these loops, positive to the right, then d phi b dt is, let's see, so B is this way, d phi b dt is negative, and it's increasing, so the change is negative, so the EMF is positive. And let's see, if the current goes around this way, that's a positive direction, so the current comes around this way. And sure enough, it goes in the opposite direction, just like it should. So the point of all this is it's not just a permanent magnet going through a loop. You can do all kinds of different setups. Anytime you have the magnetic flux changing in a loop, you'll get an EMF.